Bismillahirrahmanirrahim. Today we are going to talk about the next experiment in line, that is experiment number 7, and it deals with the Fourier series representation in MATLAB. So the learning objectives for this lab includes the construction of the complex exponential Fourier series coefficients, and along with that, how to display the line spectrum of the periodic signals. So let's dig in and find out what we have in here. The very first thing that comes into the part, that is basically the pith of the whole concept that we are going to study further, is basically includes the understanding of the periodic signals. So we all know that all those signals which basically repeat themselves after a fixed interval of time are the periodic signals, and the most important periodic signals are the real sinusoidal signals and the complex exponential signals. So the sinusoidal signals, which includes the sine and cosine signals, and the complex exponential signals, which could be written in terms of e raised to the power j omega naught t. And all the periodic signals have some fundamental angular frequency, that is omega naught, which is equal to basically 2 pi f naught, and this f naught basically denotes the fundamental frequency of the signal. So complex exponential Fourier series representation, there could be multiple representations like Fourier series, exponential Fourier series representation and trigonometric Fourier series representation. So the first one is the exponential Fourier series representation, which basically tells that x of t could be mapped in terms of the Fourier series by this formula, which simply tells that some a k's when multiplied with e raised to the power j k omega naught t and summed up over k minus infinity to infinity can give us the same signal as x of t. And these AKs here are known as the complex Fourier series coefficient, which could be computed using this formula. And basically these AKs are computed for K0, K1, 2 and so on. So if we put K equals to 0 here, what we can see is this exponential terms becomes 1, because the term in the exponent becomes 0 because K equals to 0, and then e raised to the power 0 turns out to be 1. So if we have this term with k equals to 0, and we multiply it with x of t and integrate it with respect to t over the interval minus t to t, and then ultimately divide it with t, we get a zero coefficient of the a vector, or you can say the a Fourier series coefficients. Other than that, we have the line spectrums, which includes two different types of spectrums. One is the magnitude spectra, and other is the phase spectra. So basically, as the name suggests, when you have the magnitudes of these, when you plot the magnitudes of these Fourier series coefficients versus the frequency, it gives you a plot that is basically known as the magnitude spectrum. And if you plot the angles of these AKs with respect to the frequency, it gives you the phase spectrums, and collectively both these spectrums are known as the line spectrums. Okay, let's move to the next one. We have the trigonometric Fourier series representation, where we have a naught, that is the that you can say is the DC coefficient, and this is the AC coefficient of the of trigonometric Fourier series representation. So basically, the AC coefficient includes AKs and BKs, and being multiplied with cosine and sine parts. So basically, what it simply tells that the Fourier series, the trigonometric Fourier series, is basically a sum of sines and cosines functions. Okay, so if you have been through through some mathematics courses, which you must have been through, so you must have studied Taylor series and Fourier series over there as well, where you represent the signals as an infinite sum of terms. So here you do the same. You have infinite terms for which you find out the coefficients, and then you add, and then you multiply them with the corresponding cosines and sine functions, and then you add them up over the whole terms, and then you add it to the DC part, and this whole gives you the original signal x of t. So these AKs and BKs, which are the Fourier series coefficients, could be found out using these two equations. Okay. So here one another important concept comes in, that is basically related to the even and odd functions. So in order to model the odd functions, we use all the sine terms, and in order to model the you can say the even functions, we use all cosine terms. So you can say that for the even functions, bk's are 0, and for the odd functions, ak's turns out to be 0. Okay, so we have some properties of the Fourier series. But before jumping onto the properties, here is some explanation which simply tells that the signal and the Fourier series, this input signal, basically the input signal x of t, and the Fourier coefficients AKs uh, are basically constitutes a one-to-one mapping. So if you know the original input signal x of t, you can find out what the coefficients are, and if you have the coefficients given, you can find out what the original signal is, what the original input signal is. So it's a one-to-one mapping, which basically incorporates the linearity. Okay, so let's jump to the very first um property, that is a time shifting property. So if you have the input signal x of t that maps to the Fourier coefficients a k, so and if you incorporate a time shift of t1 into your original signal x of t, so the coefficients that were ak for the x of t to ak mapping becomes something like this, that these ak's, the coefficients gets another factor with them, that gets multiplied with them. So this is how the time shifting is incorporated in the Fourier domain, and how it maps to the time domain. The next property is the time reversal property. Time reversal property simply tells that if you have a signal x of t that maps to the Fourier coefficients ak, then if you flip the signal, your original signal x of t, and it becomes x of minus t, so the coefficients that were mapping to ak are now mapped to a of minus k. Similarly, signal multiplication simply tells that you have the signal x of t that maps to the coefficients ak, and you have the signal y of t that maps to the coefficients bk, and if you multiply the two signals in time domain, the coefficients gets convolved in the Fourier domain. So this is the most simplest explanation, but obviously when you go into deeper details, you will find out that you have to be very careful while multiplying the coefficients, because they are the termed coefficients, and each term has to be convolved basically with the corresponding term of bk. So it's a bit careful, but a very precise and very correctly mapped results basically. So the another property, you can say, or another aspect of the properties could be seen through the Parseval's identity, which we have been through before as well. So this is the Parseval's identity, which simply tells that absolute squared terms, when integrated over some time period and then divided by the total time, gives us the Parseval's identity. Okay, so basically, when you move to the Fourier domain, what happens is that integral becomes that it simply tells that if you take an absolute sum as sum of the coefficients, and then square them up, and then sum them up from the first to the last terms for all the terms, then you get the Parseval's identity px. Okay, Ji. Let's talk about some of the practical aspects or some of the graphical and visual aspects of this whole thing. You have the here you have me. You can see that this this square box simply is the original signal x of t. Okay, and these signals that you can see in red, yellow, blue, and so on, green, and that is continuously evolving and moving. These are multiple terms of the Fourier series. So multiple terms are being computed, and the whole graph is being evolved and evolved and evolved. And ultimately, what happens? It gives you an approximation to the original signal. Obviously, if you keep on adding the terms, and if you add infinite terms, you can give the exact you can basically represent the exact fx of t using the Fourier series coefficients. But because of some practicalities, we cannot add infinite terms, and we cannot get the exact infinite terms result. But we can get a very good approximation using some higher number of if you can say by introducing some higher level harmonics into the system. Okay, so this is a more better picture of what I was trying to explain before. Here you can see from the legend that this blue signal basically is the n equals to 1. That means it's a fundamental period. This is the first harmonic. Okay, sorry, this is the fundamental signal that you have. Then n equals to 2, that it gives you the next harmonic. And then n equals to 5 gives you another harmonic. You can see as you keep on increasing the value of n, which is basically the k in our case. So basically, if you keep evolving this n, what it's going to do, it will keep on approaching to the original signal. So you can see that as you move n, as you basically move from n1 to n50, you can see this n1 and this n50 signal has how much difference. This n and this 50th harmonic basically gives you a very good approximation of the actual signal. So this is how we can simply keep on evolving the signal, and keep moving and keep approaching to the actual signal. And you can have any kind of signal, and every different kind of signal tell you the can give you the Fourier series representation. Like you can see here, this is your signal, this is your first harmonic. And then you keep moving, keep adding harmonics, and your signal keep moving towards the better and better and better approximation of the original signal.